Hello everyone. Today I want to talk to you about discrete time processing of continuous time signals. In many applications, you want to do discrete time processing or digital processing on the continuous time signals. For example, in your Arduino-based projects, you have a continuous time signal. You're recording the electrical signal that comes out of your transducer, or that's generated by your transducer. Or you're doing temperature recording of your thermometers. And then you have this continuous time signal. You want to do some processing on it and then generate another signal at the output. You want to average it, sum it up, or do some sort of filtering on the recorded or on the signal that's generated by your transducer. So with that, let's take a look at how this process is done. Okay. So step by step, let's review the block diagram of discrete time processing of continuous time signals. So you start with your continuous time signal xc of t. We label it, we denote it by x sub c of t. This is your continuous time signal. We need to convert this one to xd of n, which is the discrete time signal, using c to d conversion or continuous time to discrete time conversion. Basically, what it means is sampling your continuous time signal with an impulse train, periodic impulse train with period of t. Right. In the next step, after you have this discrete time system and discrete time signal, you would like to do the processing on it, so that you have a discrete time system which has impulse response of hd of n, or frequency response of uppercase h sub d e to the j omega. And then you send your discrete time signal xd of n to this system, and at the output you get yd of n, which is another discrete time signal. Okay, for the topic of DT processing of CT signals, we would like to denote the frequency in the discrete time Fourier transform with uppercase omega, like this, and use the lowercase omega to show the frequency in the Fourier transform of continuous time signals. So we have h of j omega. That's the Fourier transform of your continuous time signal, and we have h of e to the j uppercase omega to show the Fourier transform of a discrete time signal. All right, so you processed your discrete time signal, you generated another discrete time signal at the output, and you are ready to convert it back to a continuous time signal, which is going to be your yc of t. Okay, the last step is conversion of yd of n to yc of t, for which we can use a d to c conversion. All right, we're going to go look at each step one by one and try to find out how all of these processes are done. Okay. First, let's look at the relationship between xc of j omega, which is the Fourier transform of this xc of t, the relationship between xc of j omega and xd of e to the j omega, which is the Fourier transform of xd of n. All right. And this box here represents this shows what happens inside your C to D conversion. So you multiply xc of t with an impulse train, p of t, then you have xp of t, and then you have a bunch of impulses as your xp of t, which is still a continuous time signal. Then you are going to convert this impulse train, the scale impulse train, to discrete time sequence. So this picture in here, this graph shows the Fourier transform of your band-limited signal xc of t. We're going to show it with x sub c of j omega. And this is an arbitrary shape. It just shows that the spectrum is confined, so it's limited limited to some omega values, right? Xp of j omega, from the previous lectures, you know that Xp of j omega is going to look similar. The spectrum of this sample signal is going to look like the spectrum of C of t or xc of j omega, just repeated every 2 pi over t points. So we know that xp of j omega is equal to 1 over t sigma xc of j omega minus k times 2 pi over t. K running from negative infinity to plus infinity. So, okay. That's for our xp of j omega. And then we know the relationship between x of n and xp of t. It's basically using these stem format to replace those delta functions and normalizing the x-axis, the time axis. So instead of having 0t, 2t, 3t, we have 0, 1, n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on and so forth. So we are normalizing the x-axis. All right, xd of e to the j omega is going to look similar to xp of j omega. It's just that the frequency axis, the numbers on the frequency axis is going to be scaled. So you're going to have 2 pi here, 0 here, negative 2 pi here, compared to 2 pi over t1, negative 2 pi over t1. And we're going to write the equations for comparing xp of j omega and xd of j omega, e to the j omega, and you can find out how they are related. Okay, so let's write some equations for all of those Fourier transforms and the conversions, just to find out the mathematical relationship between xp of j omega and xd of e to the j omega. All right, so I know that xp of t equals to x of t multiplied by p of t. P of t is the impulse train. With the period of t, uppercase T, xc of t is my original continuous time signal. Then I know xp of t equals to sigma, it's a series of delta functions, n minus t minus nt, t minus nt. It's a continuous time signal, so independent variable is t. Then n runs from negative infinity to plus infinity. And the period of this impulse train is uppercase T. So with that, I have xp of t equals to sigma xc of t multiplied by delta of t minus nt, running for n equals to negative infinity to plus infinity. And that's going to be equal to sigma n from negative infinity to plus infinity xc of nt multiplied by delta of t minus nt, the sampling property of the delta function. All right. I also know the relationship between xd of n and the xc of t. All right, so with that, I can write xd of n equals to x of nt. xd of n is the sampled version of x of t. All right, now I have xp of t equals to, I'm rewriting this one in here. I want to rewrite this, but I want to change this one to xd of n. All right. Okay, so xp of t is going to be equal to sigma n equals to negative infinity to plus infinity. Instead of xc of nt, I'm going to write x sub d of n, because they are equal, multiplied by delta of t minus nt. All right. Okay. Now, if you remember, we had, let me add a note in here. Note. We had the Fourier transform, we saw the Fourier transform of this, the shifted delta function. The Fourier transform of delta of t minus nt was equal to e to the minus j omega n t. All right, so now we're ready to take the Fourier transform from each side of the last equation. With that, I have the Fourier transform of xp of t. It's x sub p of j omega. It's a continuous time signal, so I use lowercase omega in the Fourier transform representation. So xp of j omega equals to sigma xd of n multiplied by e to the minus j omega n t, from n equal to negative infinity to plus infinity. All right, so I found xp of j omega, and I'm hoping to use this equation to find the relationship between xp of j omega and x sub d of e to the j omega. Let's proceed and see how we can use this to find a relationship between those two. I want to rewrite the previous equation in here for you. xp of j omega equals to x of n equals to negative infinity to plus infinity x sub d of n e to the minus j omega nt. This is what we saw. Also from the previous lectures, we know that if I have the discrete time signal xd of n and I want to find the Fourier transform of it, I can write xd of e to the j omega equals to sigma xd of n e to the minus j omega n, running from n equals to negative infinity to plus infinity. All right, so if you compare these two together, if you compare this one with this one, you can see that you can get xp of j omega from xd of e to the j omega by scaling the omega variable there. In other words, for omega equal to uppercase omega divided by t, for this omega values, I'm going to have x sub d of e to the j omega equals to xp of j omega. All right. That tells me that the shape of xp of j omega is going to be similar to the shape of x and d of e to the j omega, with the difference that the frequency axis is going to be scaled with this scaling factor. I can rewrite it in this format. X d of e to the j omega equals to xp of j omega for omega equals to uppercase omega divided by t, and xp of j omega equals to x d of e to the j omega for omega values equal to lowercase omega multiplied by t. All right, now that we have our xd of n and we know the relationship between Fourier transform of this xd of n and xc of t, let's focus here. Now you have your discrete time signal and you have designed a discrete time system, or you are given a discrete time signal, a discrete time system, and it has the frequency response of hd of e to the j omega, and you want to apply this input to this system and you want to get the output. From the previous lectures, you know that y of e to the j omega is going to be equal to x of e to the j omega multiplied by h of e to the j omega. This is an LTI system. It's a discrete time LTI system. So this is a relationship between input and output in the frequency domain. I have a subscript d in here to differentiate it from a continuous time signal. All right. So let me start by drawing some spectra for the processed version of your discrete time signal. So I'm going to start with the spectrum of x sub d of e to the j omega, apply some filter on it, for example, a unity filter to this discrete time signal, and see how the output is going to look like. So I'm drawing x sub d of e to the j omega. This is my x sub d of e to the j omega. All right, so it's going to look like what I had for x sub p of j omega. All right, this point is going to be 2 pi, because I know that this is a DTFT function and it's periodic with period of 2 pi. So the next replica must be located at negative 2 pi and 2 pi, which is 2 pi point away from omega equal to 0. So the amplitude is equal to 1 over t. I'm continuing the previous example that we saw, the spectra that we saw for x sub p of j omega. All right, so I have this one, and I decided to apply this filter to it. This is my discrete time filter. This is just an example. We want to see how it's going to work out. So I have this filter. It's going to look like this. It's everywhere other than omega above negative omega c, beyond omega c, and beyond negative omega c. So when omega is between negative omega c and omega c, the amplitude of my filter is equal to 1. And this is my h. I'm overlaying h, the graph of h sub d of e to the j omega. All right, so I have this filter applied to this signal. It is also a DTFT, so it's going to be periodic. So I better draw another replica in here. There's going to be another replica in here. The amplitude is 1. The amplitude is 1. All right. So I know that y of e to the j omega is multiplication of these two. So I'm going to multiply these two together, and these are 0. Whenever the amplitude of h d of e to the j omega is 0, it's going to be, that 0 is going to be multiplied by the amplitude of xd of e to the j omega, so that's going to zero it out. So if I go and draw the graph of y sub d of e to the j omega, I'm going to have something like this. Y sub d of e to the j omega, which I know y sub d of e to the j omega equals to x sub d of e to the j omega multiplied by h sub d of e to the j omega. All right, so if I do that, I'm going to end up with this function. Let's use this color to extend this line. So we are matching the frequencies. All right, so here, let's try it with maybe green color. So I'm going to have something like this, because I'm multiplying every point on the top graph for xd of e to the j omega by 1 or by 0. So this is the resulting graph. Whenever the amplitude of xd of e to the j omega, the amplitude of yd of e to the j omega is going to be equal to 0, and this is 2 pi point. Again, yd of e to the j omega is going to be periodic with period of 2 pi. And this is here. Okay, so this is negative 2 pi. All right, so good. So that's my yd of e to the j omega. The maximum amplitude is going to be 1 over t, which is this 1 over t in here multiplied by 1. And the same goes here. This is 1 over t at this point. 1 over t here and 1 over t in here. All right, so I am ready to find the spectrum of y sub c of j omega, which is going to be calculated by sending this signal to D to C converter. So it's going to go here. I'm drawing, this time I'm drawing Y sub P of J omega. And this is going to come here. Actually, I don't need this one. So let's move it because I'm scaling the x-axis. To draw the graph of x sub y sub p of j omega, I'm going to draw the same spectrum and then work out the numbers on the x-axis or the frequency values. And the shape is going to be similar. The numbers on the x-axis or the frequency axis are going to be different. So this one is going to be equal to, so here I had omega c and negative omega c. And for the graph of yp of j omega, I'm going to have omega c divided by t and negative omega c divided by t. This one is going to be 2 pi over t. This is the scale version of the numbers on the frequency axis of the discrete time function. So it's negative 2 pi over t. All right. The amplitude is going to be the same because I'm only scaling the x-axis. All right. So that's good. And then I need to filter this one. I need to send it to a low-pass filter so I can only extract one part of this spectrum, this one. And then I can do I can find the inverse Fourier transform of that one. So I'm going to send it to a low-pass filter. This is my low-pass filter, so I can remove the extra copies. So I can choose a low-pass filter with cutoff frequency less than half of this 2 pi over t or less than omega s over 2. Omega s is your sampling frequency. So you remember it's about the Nyquist rate. So I'm going to use pi over t and negative pi over t as the cutoff frequency for my low-pass filter. This is h of low-pass filter of j omega. This is a continuous time filter, all right? So I can do that, and then at the end, I'm going to get my yc of j omega back. So, okay, it's going to look like this. So omega c over t, negative omega c over t, and this is 0 everywhere else, and I have omega as my x-axis. All right, so I got my omega c sub j omega back, and then if I choose the amplitude of this filter as t, then the amplitude of this one is going to be equal to 1. This amplitude is going to be equal to 1. Okay, this is the block diagram representation of the discrete time to continuous time conversion unit. So it takes your discrete time signal yd of n, and then it converts this discrete time sequence to impulse train, results in yp of t, then sends it to a low pass filter with cutoff frequency omega s over 2. Omega s is the sampling frequency of your impulse train that you use to sample your xc of t, and then generates a continuous time signal yc of t. So as you saw in the previous page, y sub d of e to the j omega was equal to y sub p of j omega for omega equals to uppercase omega over t. As a result, y sub c of j omega is going to be equal to y sub p of j omega for absolute value of omega less than omega s over 2. And for other omega values, it's going to be equal to 0. So I'm going to take only the central part, the central section of my spectrum for yc of for yp of j omega. Okay, thanks for listening, and thanks for watching the video.